I already committed a capital sin by not wearing my name badge, but as Peter said, I'm Jan Vonk, and there's also Eugenia Rosu, who is somewhere in the audience. Oh, there she is, yeah. And so together we'll be doing this course on complex multiplication. So complex multiplication is maybe a little bit of the odd one out, because it's not a subject that is overtly statistical in nature, at least not at first glance. But rather, maybe you should think of it as a very powerful tool. It's one of the most powerful tools that we have in number theory to attack a variety of arithmetic questions. Now, the subject of complex multiplication has a very long history. It goes back even further than all the old dates that Peter already wrote on the board, and has really its origins maybe in the mid-19th century, so a very long time ago. And it's gone through a whole evolution since then. And so classically it arose in the context of class field theory, so dealing with the kinds of problems that Peter ended with, constructing explicitly ring class fields and solving the problem of representing primes by quadratic forms. But then sort of in the 1950s, this new era came up, and it started really with the work of Heegner, who solved the class number 1 problem using this idea of rather changing the point of view to the arithmetic of rational points on modular curves, which then later on has become a tremendously important idea. And so in particular, we'll talk a little bit about singular moduli and elliptic units. These elliptic units were used by Coates and Wiles in 1976 to prove something about Burton-Swinnerton-Dyer in analytic rank 0 for CM elliptic curves. And then very spectacularly in the mid-80s, Gros and Zagier used these kinds of ideas looking at factorizations of singular moduli, so the arithmetic properties of the invariants we'll construct to prove one implication of the Burton-Swinnerton-Dyer conjecture in analytic rank 1 for elliptic curves that don't need to have CM. So a lot of really spectacular applications. There's so many faces and so many sides to complex multiplication that you should never confine yourself to just viewing it through one lens. And that's one of the things we'll try a little bit in this course. There's so much to say that we have to pick and choose a couple of aspects to talk about, but we'll start, I'll start with the more classical approach, and so the more analytic approach of the German school really early on. And then later on, Eugenia will adopt slightly more modern viewpoints coming from maybe methods of Hecke to do with L functions and Shimura reciprocity. So we hope to sort of cover different viewpoints of this magnificent theory and give you some ideas of what it can do. And I'd like to begin very classically with a viewpoint that is really due to Eisenstein. And what I'd like to do is I'd like to take a step back and introduce some of the ideas in a way that I think greatly elucidates the theory that comes later for elliptic functions, which is really what I'll talk about today. But I'll start with cyclotomy, and I recommend forgetting everything you know about trigonometric functions. So expunge them completely from your mind and pretend that you're coming at this completely fresh. And let's see what we can learn. So what we'll do is we'll consider the setup where we have the inclusion of the integers inside of the real numbers. And I would like to talk about the quotient, R mod z. Yeah? And so we think of this intuitively as a circle group. And what we'll want to do is we want to embed the quotient algebraically. We want to view the quotient as an algebraic variety. And so the picture to have in mind here is that we have the line with the discrete set of integers on it, and we want to take the quotient, so where all the points are contracted down to 1. We want to view this as a very nice algebraic set of a projective space. And so what we need to do is we need to construct functions on the real line that are invariant under translation by z. And so how do you do that? The most straightforward way to find invariant functions is to average over this group action. And so we're going to define functions which I'll call alpha kz, which will be obtained by summing over the integers a function with rapid enough decay for which I'll take z minus lambda to the k as long as k is at least 2. When k is at least 2, this series converges absolutely. In fact, it converges uniformly on compacts away from these lattice points. And so this defines for us an invariant function under translation by z. And this is very nice because we have an infinite collection and we can plug in any k we like. And so there's various relations satisfied by these alpha k's. And so I'll say that many polynomial relations exist. For example, if I take alpha 2 and I square it, I get alpha 4 plus some coefficient, which I'll call omega 2, times alpha 2. That's one of the relations we get. Where in general, all the polynomial relations that we find involve these constants omega, which I'll define for you, where the coefficients are combinations, let's say, of the set of constants omega k, which is where I take the same lattice sum. I'll omit 0, and I'll use this symbol for the remainder of these lectures. Whenever I have a group, the group prime means the elements. Sorry? Write bigger. Okay, I'll try and write bigger, yeah. And please feel free, this is a recurrent problem when I lecture, to remind me periodically to write larger, because I might forget. So whenever I have a group, the set of non-zero elements I'll denote by that group prime, so this will come back. And here the sum is just what you think it is, 1 divided by lambda to the k. Yeah, of course, we recognize these as special values of the Riemann zeta function, but because there's enough zetas in this story, I will not use this symbol at all. Okay, now how do we find all polynomial relations? Now the claim is that the nature of all of these relations and also the nature of the constants that occur is best understood by doing two operations to these kinds of series. The first one is to go just outside of the range of absolute convergence. So we're going to want to deal with k is equal to 1, where this sum does not converge absolutely, and we're going to want to fix that. The second step is to lift multiplicatively that series that we define just outside the range of absolute convergence. Those are kind of two important steps that come up in this theory time and time again. So the first one is to consider the case where k equals 1. And the case where k equals 1, what we could do is we can define it pretty much the same way. So we define alpha 1 of z to be the sum over all integers of 1 over z minus lambda. The only problem being that this does not converge absolutely. If you expand this as a geometric series, you see that the leading term is just the sum of the 1 over lambdas, which diverges. So what we're going to do is we're just going to remove that from the sum and start with the next term, which is easily achieved by adding in this correction term 1 over lambda. And of course, for that to make sense, I'd better assume lambda is not 0, so that term we're going to be considering separately, like so. Okay. Now this function now does converge absolutely and gives us, as you may check, a translation invariant function. The translation invariance is maybe slightly more involved than there because we have this additional term, but you'll see that the partial sums, the difference of them goes to 0, and you still get a translation invariant function with poles along the integers, of course. And it satisfies the following relation. If you take alpha 1 and you square it, you get essentially alpha 2. If you remember to subtract 3 times omega 2. So this relation we'll use again in the future, so maybe let me give that its own box as well. how does it work again? If you have 3 boards, which one are you supposed to write on first? I always forget. Ah, yeah, it's too late. But the next one, I go for the middle one or the back one? Middle, okay, very good. Thank you. All right, so that's the first step. The second step is to consider this function, alpha 1, and to lift it multiplicatively. So what we're going to do is we're going to find a multiplicative lift and I mean, for a multiplicative lift, I mean a lift for the function, or the functional, which I'll denote by d log dz, which sends a function to its derivative divided by the function itself. So we're going to want to construct a multiplicative lift for this operation of this function alpha 1. And in fact, given this infinite sum expression, you can do this formally, immediately write it down, such a multiplicative lift, by defining sigma of z to be the product over all non-zero elements of the group z, with this additional factor 0 taken out as well, of the function 1 minus z over lambda, whose logarithmic derivative will give me these guys. And for the terms 1 over lambda, I better also add an exponential term, which is z modulo lambda, like so. Okay. So now we get a very nice infinite product function. Convergence, again, works out, and it has the following beautiful properties. Well, first of all, as promised, its logarithmic derivative is this function alpha 1 of z that we had before. And second of all, maybe it's also worth noting that this function is odd. And from the oddness follows that if you translate it by 1, it's no longer invariant, but it almost is. It's invariant up to a sign. So if you translate it by 1, you find that in fact it's no longer invariant, but it is when you put in the minus sign. So there's a factor of automorphy really for invariance, which in this case is a very benign one, but still it being non-trivial is significant in what is to follow. You know? So these properties you can check formally. The second one follows from the oddness of this sigma function. All right, what do we do with this? Yeah, we have all these functions, we have these relations, so this gives us really some algebraic set that we can map the quotient to. But there's 2 sides to the story. So first of all, what are these functions? They're very familiar functions, in fact. We've just put them in this guise and used notation that looks a little bit alien to us, but we know all these functions quite intimately. And so the first aspect, which historically was a very important one, is the nature of these periods, omega k, which can really be understood from this infinite product. How so? Well, Euler was the first to realize, this was around the 1740s, oh, bigger, okay. So he realized that sigma of z, there is space, yeah, exactly, yeah. Aha, okay, just font size, okay, I'll work on that. Okay, first I'm going to do something slightly mysterious because I see I forgot a factor here. You see, this multiplicative lift, it's well defined up to a constant, which is killed by the logarithmic differentiation. So I could have put in for free some constant here, whichever one I liked, and these properties would still be true. Let me actually make use of that flexibility and add in a factor pi for reasons that will become apparent immediately. So Euler realized that this particular infinite product is a familiar ally. It is the sine function evaluated at the argument pi times z. That's what Euler realized. And you can kind of see why this is believable, right? We have this transformation law. This is familiar from the sign. Also, this function has zeros precisely at the lattice point z. So if both were polynomials, which they're not, the quotient would have to be constant, and then you can determine that constant to see that it comes out to be precisely 1 in this case, or 1 over pi if you hadn't put in the pi. Yeah? That argument can actually be made rigorous in the complex analytic setting by viewing them as holomorphic functions and using the Hadamard factorization theorem, which is really the way to make that proof rigorous. So we have this identity, which was first realized by Euler. Now, what do we deduce from this? This gives us very valuable information, because the function alpha 1 of z, if you expand it out as a Taylor series in z, you just get the generating series for the omega k's. Like so. On the other hand, alpha 1 of z is the logarithmic derivative of sigma, which is the sine function of pi z. So this function is also equal to pi times the cotangent of pi z. Yes. And if you're Euler, it's pretty natural to use Euler's formula, which is, it says that e to the I theta is cosine theta plus I sine theta. And if you do that, you rewrite this expression as minus pi I times e to the 2 pi I z plus 1 divided by e to the 2 pi I z minus 1. Now this function also has a nice Taylor expansion, which we can expand out and solve for the coefficients, and we see that this is of a very different nature than what we had before. It's very explicit. It's just exponential functions. And the generating series that we find is one for Bernoulli numbers. I didn't use the buttons. Maybe that was a mistake. So we deduce from this the value of these omega k's by just equating all of the coefficients of this Taylor series to each other. So we find that omega k is just 2 pi to the power k divided by k factorial times the absolute value of the kth Bernoulli number. So this is a Bernoulli number, which is essentially by definition really. You can define the Bernoulli number to be the number that makes that come out. What's important is that there's a nice recursion relation for it. They're very computable quantities, and they're rational numbers. So these are the Bernoulli numbers. Now this discovery made Euler famous overnight at a very young age. And it certainly is a fascinating story, and these periods in this case are not so difficult to understand because they're all rational multiples of the kth power of pi, essentially, and we know precisely which rational multiple as well. Okay? It's a fascinating story, and there's a lot to say about periods also in the context that we're going to discuss, but we're going to focus rather on a second kind of theme. So this is, I should maybe say, for k at least 2. Yeah. And the second theme that I want to focus on, so these periods I just mentioned, will be the main topic, is that of special values.
Wait, doesn't k have to be even?
Well, if k is odd, then both sides are 0.
Oh, okay.
Yeah. So the formula still holds, it's just not very interesting. Yeah. All right, so the special values. We have a bunch of functions, right? So which function are we going to consider the special values of? And what is a special value? So what we're going to do is we're going to consider values of all of these functions at division points. Of the quotient R mod z, i.e. at arguments z which are in Q mod z. Those are precisely the points of finite order in the quotient, and we're going to want to evaluate these functions at such points and see what comes out. Now, of course, the cat's out of the bag. We're dealing with cyclotomic functions, we're dealing with trigonometric functions, so we know very well what to expect because we know these functions so well. Now, which functions are we going to be considering? This is where we have to be a little bit strategic, maybe. And I'm going to use two colors. So we have this lattice where I'm going to color the even ones and the odd ones in a different color. So green and white, hopefully, will do. And so what we could do is we could say, well, we have these invariant functions, the alpha k's. We also have the alpha 1, and we have that fundamental relation that's up there. So what we could do is we could embed the quotient algebraically using that fundamental relation. So you're going to consider the function, let's take alpha 1, so z goes to alpha 1 of z, comma alpha 2 of z, which would give us a very nice algebraic subset of the projective plane with that equation. So it looks like a parabola, where the lattice points have all been relegated to the point at infinity, and the equation is just y equals x squared minus pi squared. Yeah, actually 3 times omega 2, but we know that's pi squared now. Okay, but you say, that's crazy. Why would you do that? Why would you take this awkward embedding? Because, of course, we all know cyclotomic functions. We would much rather view this as something like a circle, right? We would much prefer to use the cosine and the sine function than we would to use this alpha 1 and this alpha 2. And that gives us really an alternative way to view this quotient, except it comes at the cost of these functions, sigma, not quite being invariant. They're only invariant up to this factor of automorphy, which is minus 1 in this case. But never mind that. We can still consider the pair of functions sine and cosine, which we now know is sigma of z, and then the cosine is just sigma shifted by 1/2. Yeah? And so remember, this shift by a 2-division point will come back later on. Okay? So if we take this pair of functions, we're also describing something algebraic, except it's not quite an embedding of the quotient because of this lack of invariance. So the odd and the even lattice points do not go to the same point. And we get this kind of picture, where now the equation is much simpler. It's x squared plus y squared equals 1. Yes? And you can very easily figure out what the map is that goes in this direction. Okay? Now, this is very much the 2 points of view that later on for elliptic curves we'll also have, where this is the way that Weierstrass liked to think about elliptic curves, and this is the way that Jacobi liked to think about elliptic curves. And I'll say something about that in a second. So we have these 2 viewpoints. If you're familiar with trigonometric functions, which we all are from a young age, you would probably vastly prefer this one. It looks much nicer. It has an algebraic equation. It doesn't have these transcendental periods coming up as the coefficients, etc. So in some ways, this one feels much more natural, which is also true when we look at these special values at division points. Yeah? Because I promised you we're going to look at special values at division points, so z in q modulo z, and I'd much prefer to take these. Yeah? You can also take alpha 1, but that's pi times the cotangent of pi z. So that's not really going to be algebraic until we divide out that period. So here, these special values are algebraic numbers. And in fact, we can figure out a lot about the arithmetic of these special values. I mean, we have, for instance, the Chebyshev polynomials, which won't really be super important for what follows. But they're polynomials defining the cosine of n theta as a polynomial in the cosine of theta. So these polynomial relations are expressed by the Chebyshev polynomials. And by slight variance, you can quickly find very nice polynomials for the special values of this sigma function. So we find that the values of these sigma z at division points are algebraic. In fact, they're much more specific numbers than just algebraic numbers. We can say a lot about their arithmetic. So, for example, to name one also that has some historical significance, we could take the division point 2 divided by 17, yeah, for example. And for 2 divided by 17, well, we get the sine of 2 pi divided by 17. So the value that we get is zeta 17 plus zeta 17 inverse, and that may be divided by 2i. Well, that factor is elementary, we won't care so much about it, but this element certainly is very interesting. So the first thing to note is that it's an element that's algebraic, and it lies, in fact, in an abelian extension, where you join a 4 times 17th root of unity to Q. So it lies in an abelian extension of Q. And also its prime, oh sorry, this should be a minus, also its prime factorization is concentrated really at one particular prime, which is 17. So if I call this field K, it is, what it is half, I guess, of a 17 unit. So i.e. it's contained in the ring of integers where I invert 17, and then it's a unit. Yeah. Larger, yes, thank you. Yes. Okay. Sorry?
Seriously, rewrite that part larger because
The
68 is like...
oh, this thing. Thanks for telling me that's 68, by the way. Yeah. Okay. Anyway, so this is our motivational picture. We haven't really learned anything new, but we have introduced points of view that will be tremendously important in the context of elliptic functions, and which I hope will make all the constructions seem very natural. Okay. So, by the way, I should mention that an explicit expression in terms of radicals for this particular number was found by Gauss, famously, when he divided the circle into 17 points, which is what cyclotomy means, by the way. The circle and the tomy part comes from temne, the Greek word for cutting it. So it's cutting the circle in 17 points. Okay, now what we're going to do is essentially we're going to repeat this, but in the more rich setup of elliptic functions. And for elliptic functions, we're going to consider a lattice which will be generated by two elements, omega 1 and omega 2, in the complex numbers. And we want to do essentially the same thing. This time the picture looks a little bit more complicated. We have this grid inside of C, and it's going to be generated by a pair of elements, omega 1, and let's say omega 2. And they form a lattice which I'll call lambda. The quotient, again, let me maybe draw it here downward. We want to think of as a donut, and we would like to embed it, topologically it's a donut, we would like to embed it as an algebraic variety in some smart way. And so we're going to repeat those steps. So the first thing we're going to do is we're going to find invariant functions in precisely the same way. But now the choice of lattice more profoundly matters than before, because all the lattices were the same up to rescaling in R. Now I'm going to take this lattice lambda as part of my notation for the function alpha k, and I'll do exactly the same. I'll take the sum over all of the lattice points. I'll take this expression. And for this to absolutely converge, now of course I'm adding up more points, yeah? So there's an order of magnitude off. I have to assume now that k is at least 3 for this to absolutely converge and define for us an invariant function, and so therefore a function that descends to the quotient. Yeah? Okay, again, many polynomial relations exist between these, and many were found already by Eisenstein. We're going to do essentially the same steps that we did before by first going outside of the range of absolute convergence. So there before we had the alpha 1, now we have the alpha 2 and the alpha 1. Yeah? So there's 2 more steps to take. And then we're going to consider multiplicative lifts for the logarithmic derivative map and study special values at division points of those functions. Yeah. Okay, so outside the range of convergence, we defined? Well, we're stuck at 3, so we have to start with alpha 2. And alpha 2 lambda z, similarly to what we did before, z minus lambda squared is what we would like to define. But unfortunately, the 1 over lambda square as lambda ranges, sorry, I don't know why I did this, but it's just lambda here. Huh? So the sum over all the lambdas here, that's not going to converge. The leading term now is 1 over lambda squared, which, because we get an extra order of magnitude lambda if we sum over this extra dimension that we have to also remove, which we do in the same way that we did before by considering these. And because I have a 1 over lambda square, I better take the 0 term separately. Yes. Now this is an invariant function. It's absolutely convergent. It's invariant. You have to check that it's invariant. Essentially, it's the same trick as before. The difference between the partial sums will go to 0 rapidly enough. And so it's an invariant function, which, if you've read other books, it's usually referred to as the Weierstrass P function. It's a very famous function. It's named after Weierstrass, but really Eisenstein already had these in the bag before him. Now, we're not quite done yet, right? Because the range of absolute convergence is a little bit smaller. We also have to go all the way to alpha 1, which we do in the same way, but now we're going to have to subtract 2 terms. So again, the 0 term will be separate, and then we take 1 over z minus lambda. We also have to add the 1 over lambda, the offensive linear term, but also the quadratic one will need to be corrected. And so we also have to add in this particular z over lambda square, the 2 first terms in the Taylor expansion of that guy. Now we're a little bit in trouble because even though it converges, it's not going to be an invariant function. Even if we can rearrange, you'll see that there's no real reason for the partial sums to go to 0 in any interesting way. And in fact, this is not an invariant function. So already with the alphas, we're in trouble. Yeah? Before, at least the alphas were all invariant, and the sigma was going to be the one that failed invariance. Here already, the alpha 1 is not invariant. And again, to tie it up with the literature, this is often called the Weierstrass zeta function. Okay, now it's not invariant, so maybe we should give a name. To the lack of invariance. If I take alpha 1, lambda, and I shifted by one of these 2 bases elements, where are they? Here, omega 1 or omega 2, it's going to be invariant up to a constant function, which you can see because the derivative of alpha 1 is alpha 2, which is invariant. And but that constant doesn't need to be 0, and we'll call it a to I. Yeah? These are the periods of this function alpha 1. I'll need them a little bit later in my notation. Okay, now how am I going to do this? I think I want to bring this to the top, is that right? Like this? Tell me if I'm doing it wrong. Yeah, that's true, but I thought it's maybe a bit low if people want to. And now this one comes down. Nope. This one. Okay. All right. Okay, so that was the first step. We've now defined satisfactory functions, the alphas. And again, they satisfy a variety of polynomial relations between them. In fact, I don't know if I want to tell you about one already. No, I'll do that later. But we still need the multiplicative lift. Yeah? So for the multiplicative lift, so the thing that'll generalize the sine function, will this time be given by something which I'll still call sigma, but maybe I'll use this kind of sigma, which is more traditional. It depends on this lattice lambda. This time I'm not going to put this constant in. I'll just do z this should be lambda in lambda prime, 1 minus z over lambda, just like before. So the logarithmic derivative gives us the first terms that appear there in the alpha 1. And now we also need to account for these correction terms, which we'll do with this exponential factor, which is z divided by lambda plus z squared divided by 2 lambda squared, whose derivative, logarithmic derivative, will give us precisely those two terms there. Yeah? In principle, we're free to put in a constant, but I'm not going to do that here. Okay, now, it satisfies, just as before, the fact that the logarithmic derivative of this function sigma, which is sigma prime z divided by sigma z, this is how we constructed it, is going to give us back, sorry, I forgot to put the lattice in the sigma notation, but hopefully that's clear, is this alpha 1 of the lattice and an argument z. The second part is more important in that we've lost invariance by doing this multiplicative lift, and we've lost it in a much more serious way. If we take this sigma function of the lattice and we evaluate where we translate by one of the basis vectors omega I, so I is 1 or 2, then we get, again like before, a minus sign, and then we get also this exponential factor, which is eta I, the period of the function that I just wrote down, plus z shifted by omega I over 2, times the original function. So you see, again, we've lost invariance up to an automorphy factor which we can understand very explicitly, but it is much more serious than before, and in particular, it's not, the minus 1 was always an algebraic number. Here we get this kind of exponential factor. So we have to do something slightly more serious than we did before with the sine and cosine function to correct for this. You can prove this essentially in the same way that you did for the sine function, before you knew it was the sine function, by the oddness of the sigma function, and then evaluating again exactly at minus omega I over 2 to get this transformation law, coming from the transformation law of its logarithmic derivative. This one kind of takes care of itself, apparently. That's good. Okay, so now we come to the main goal at hand, the special values. And this is really what we'll study in this course. I'm not going to say much about the periods, there's much to say about them as well, but we're going to focus on the special values. And again, we're going to take values at division points, so points of finite order of the lattice, of C modulo the lattice. And of course, a very important question now arises, which functions do we consider? And if we have this kind of picture in mind, we see that we could do it with the alphas, which will give us Weierstrass's model, or we could do it with these sigma functions, which will give us Jacobi's point of view, and maybe the latter seems a little bit more natural. So I'm going to make a little picture here. So I have my variable, which I'll call z in C, and C contains this lattice, like so. The first thing we can do is to take the functions alpha 2 and alpha 3. Now these functions satisfy a polynomial relation between them, which was discovered by Eisenstein, but usually goes by the Weierstrass equation for this elliptic curve. And it goes as follows. So in this model, so we get the familiar picture of an elliptic curve embedded into P2, where all the lattice points, again, have been relegated to the point at infinity. And the equation for this particular one is y squared equals x cubed minus 15 omega 4 lambda x minus 35 omega 6 lambda. Yes, thank you. Particularly this. Oh, but the equation, it doesn't really matter. I'm not going to use it again. It's a cubic equation that gives a relation between alpha 2 and alpha 3, and the coefficients are essentially these omegas, so the same definition as before, where you just take the period where you sum over the whole lattice raised to the power minus 4 in this case and minus 6 in this case. Yeah? But the point is, they're going to be transcendental numbers. We don't expect these to be algebraic in any way, in the same way that the omega k's before in the cyclotomic setting were just powers of pi. Yeah. Okay, so this is alpha 2. I'll write this bigger because that's maybe good to know. Alpha 2 and alpha 3. Which were invariant, right? Alpha 1 wasn't. Yeah. Okay, now what's the alternative? We could instead work with the sigma functions. And if we look at what we did before, we took the sigma function, and we wanted the sine and the cosine. And we got the cosine from the sine by shifting by a 2 division point. We could do the same thing here. We could take the sigma function and shift it by a 2 division point, of which there are now 4 options, right? Because we're in this higher dimensional lattice. Now, of course, there's some complication here. So we're going to consider the 4 tuple, really, of sigma lambda. I'll relegate it here to the index to make the argument more clear. We could also take sigma lambda of z plus omega 1 over 2. We could also take sigma lambda of z plus omega 2 over 2. And we could also take sigma lambda of z plus the sum of the 2 lattice points that generated divided by 2. Those are all the 2 division points that we can shift by. Now, we're still not really in a good situation because before, I mean, they lacked invariance, but only up to this sign, which is why we got away with not really doing anything additional. Now we also have this exponential factor coming up in the periods of this function. So the automorphy factor here is much more complicated, but it's an elementary exercise now to try and correct it so that at least the automorphy factor is the same for all 4 functions. Yeah? I'm not going to write down the expression, but you can get it yourself from this. So I'll write that with a dot. So a suitably normalized version of these sigma functions, like so, to make sure that their automorphy factors are all the same. Yeah? So I insert this exponential factor. Once I have that, I get a well-defined point in projective space. Now, what is the locus cut out by the equations satisfied by these? I'll try and draw this. So maybe it looks a little bit like this. So, where the intersection now, I'll draw it in blue, is the intersection of 2 quadrics in P3. In fact, they're both cylinders, as I've suggested here in this picture. And then here also in the back I have some intersection. Yeah? You can be explicit about the equations as well, but they're not really going to matter. It's just motivation, really. And you can work out also what the maps are between those. They're essentially equivalent ways to view elliptic curves. I'll tell you what the equations are. So here the equations will be of the following shape. X squared plus y squared equals 1. Great. But of course I have an extra variable, so this is going to define for me one of these cylinders. Yeah? The second equation has a parameter k in it. It goes as follows, plus something called k squared times x squared equals 1. So you get a set of 2 equations in P3, which is often referred to as the Jacobi model of an elliptic curve. Yeah. And again, we can pick our favorite, right, to study special values of. We can do it here, but maybe in hindsight, knowing the story for cyclotomic functions, that was a little bit unnatural. Maybe we prefer to work with these sigma functions instead. Yeah. And that's essentially what we're going to do in this course. So I'll say a little bit about this k. The k is a constant, which depends on the elliptic curve. This k squared is essentially the lambda invariant. And it's going to turn out that for very special elliptic curves, that's an algebraic number. So that at least we were in a situation like before where the equation that we used to cut out this elliptic curve is algebraic. And this is called the elliptic modulus, this k. I have permission to use the regular eraser. Okay. All right, so this is really what we're going to aim to do, I guess tomorrow, is guided by our cyclotomic adventures. We will study values at division points of these functions. But one thing we should acknowledge first is that we have this additional variable, which is the lattice. And it seems completely unreasonable to expect that these division values are always going to be algebraic if we're allowed to vary this lattice in some transcendental way. That seems completely absurd. So we're going to want to restrict to very specific lattices, which are the lattices with complex multiplications. So we will study the values at division points when lambda has complex multiplications. So i.e., if we look at the set of all complex numbers that multiply lambda into itself, this is a set which always contains the integers, and we're going to consider sets where this inclusion is not an equality. Yeah? So in this case, lambda defines an ideal in some order in an imaginary quadratic number field, and those will be the lattices that we consider. More specifically, we will study two kinds of invariants. The first we'll study, tremendously important, are the singular moduli. So they're values of the j function at such lattices. J function having an elementary expression in terms of these omega 4s and omega 6s. Well, maybe I should just write it down instead of saying it. So it'll be 60 omega 4 lambda cubed. It's a little bit ugly. Maybe I shouldn't have done that. Anyway, here it is. 60 omega 4 lambda cubed again. And then you have to subtract 140 omega 6 lambda squared. That's what that number is. That's the J invariant of this particular lattice. The formula doesn't matter. We'll work with the Q expansion next time, which I'll define for you tomorrow. So these special values, so this is the J invariant. They're really remarkable. And in the context of the story that Peter just told us, it essentially compensates for the fact that we're going to find algebraic numbers which don't lie in abelian extensions of Q as they did in the cyclotomic setting, but in abelian extensions of the field of fractions of lambda. So they lie in abelian extensions of imaginary quadratic fields, and imaginary quadratic fields can sometimes have extensions that are completely unramified everywhere. Those extensions you get by adjoining the values of this J function, and in fact, you get a whole infinite class of much larger fields called the ring class fields out of special values of these singular moduli. Now, one thing to note about them is that they're extremely rich, arithmetically speaking. They have prime factorizations which are so rich, they have lots of different primes we'll see, and we'll study them in what follows, that gave rise to very important developments in mathematics. And so we'll study these singular moduli for such lambda and generate ring class fields, essentially solving the problem that Peter ended with, which is the problem of representing primes by quadratic forms. Now, this one is a little bit of a bonus, which we didn't see in the cyclotomic case. In the cyclotomic case, we also studied the division values of these sigma functions. And so here also we can do that, except the automorphy factors are more serious, so we have to take appropriate quotients of these sigma functions. Now, if you do that here, you get exactly the Jacobi elliptic functions which Jacobi used, and many people were using in the classical era. So we'll also study quotients of sigma functions, which in general is the subject of Klein forms and Siegel units, which we'll only do a special case of, and we'll look more specifically at the Ramanujan delta function hit with the weight 12 slash action of a matrix gamma divided by delta rather, where gamma will be some integral matrix with some determinant, and the determinant will be prime in the cases that we study mostly. So these are called singular moduli. These special values that we get here are a case of elliptic units. And there's important relations between them, but their arithmetic is very, very different. They're not at all as rich as the singular moduli. Their prime factorizations are usually focused and we'll focus on the case where this has prime determinant at that particular prime. So they're p units, a little bit like what's on the board here. We find these p units with very rich arithmetic, but the factorizations are a little bit poorer than those of singular moduli. So there's a clear dichotomy between the two, which we'll see reflected in the size of the particular modular polynomials that we're going to write down tomorrow. And so I'd just like to end by repeating again the rightful place of these developments, or at least some of the many roles that they have played since their inception. Because everything I'm going to say will take place in the classical era, but we will be remiss not to mention the more modern developments for which we won't have time, that started really in the 1950s. For example, there was Heegner's very important paper from 1952, which took this subject really in a slightly different direction, and maybe nowadays we understand this best in the geometric context of rational points on modular curves. So he used CM theory, he used all these arithmetic values of modular functions to construct essentially what we understand nowadays are integral points on modular curves. More specifically, the curves relevant to his story are the non-split Cartan curves, if you've encountered these before. Yes. Thank you. Yeah. So this is n as the non-split Cartan curves, maybe with some prime level structure. And he used the arithmetic of these solutions, or the fact that you can give explicit equations for such curves and just solve them a priori to solve the class number 1 problem, which is a problem that was conjectured by Gauss that there's precisely 9 negative discriminants of class number 1. And so Heegner used these kinds of techniques to prove that. And this was really the start of the more modern era. There was also the work of Coates and Wiles in the context of the Birch-Swinnerton-Dyer conjecture. And what they did is they used these elliptic units and p-adic properties of these elliptic units in the context of the Birch-Swinnerton-Dyer conjecture in analytic rank 0. So that's the first kind of invariance that we studied here. And so this is really tying them in with special values of L functions, which is a topic that Eugenia will pick up later this week as we enter the more modern era. The former, the singular moduli, are arguably much more rich, as was showed in a spectacular way by the work of Gros and Zagier. In 1985, what they did is essentially they determined the factorizations of these singular moduli. Bigger? Yeah. And more generally, of differences of singular moduli, which enabled them in their later work to find explicit expressions for the height pairings of Heegner points on modular curves, and ultimately that gave them one implication of the Birch-Swinnerton-Dyer conjecture in analytic rank 1. And so really the connections between CM theory and L functions is tremendously important for the development of the field, and I'll try and sort of end on that in the third lecture if there's enough time with a brief discussion of the Kronecker limit formula. Okay, so with that said, I hope it's a little bit clear where we're going to go. So next time, which is tomorrow, I will tell you about the algebraic nature and the arithmetic properties of those two specific types of invariance. And I think I'll end there.